Now, we shall start module 2 of chapter 7. In this module, we shall discuss about the Frenet formula for the curves on a surface. From the existence theorem of a space curve, we know that for any two functions kappa s and tau s, there always exists a space curve, and if tau is 0, then for the curvature kappa s, there always exists a curve on the plane. So, we can study the nature of the curvature of a curve on a surface, and we shall find the geodesic curvature of a curve on the surface. So, in this module, we shall learn about the Frenet formula on surface, and from there we shall deduce the geodesic curvature. From fundamental theorem for curve on a surface, we know that if kappa s be a continuous function of a real variable s defined in an interval 0 less than s less than equal to a, then there exists a curve on a surface for which kappa is curvature of that curve. Now, from the first fundamental form of a surface, we know that ds square equal to a alpha beta du alpha du beta, where a alpha beta is the coefficient of first fundamental form and which is a covariant symmetric tensor of rank 2. Now, from that equation we can get a alpha beta lambda beta equals to 1 just by dividing by ds to the above equation. We get the expression 1, where lambda alpha is equal to du alpha ds, which are the components of unit tangent vector to the curve on the surface. Now, taking intrinsic derivative of 1, we get a alpha beta del lambda alpha del s lambda beta equals to 0. Actually, we are getting twice of this expression, and from there we get a alpha beta del lambda alpha del s lambda beta equals to 0. Now, from that equation we can say that either del lambda alpha del s equal to 0 or del lambda alpha del s is orthogonal to lambda beta. Now, first we consider del lambda alpha del s equal to 0. Then we see what happens. From the definition of intrinsic derivative, we get lambda alpha comma beta du beta ds. That means, lambda alpha has been done a covariant differentiation with respect to u beta with the inner product of du beta ds. Now, from the definition of covariant differentiation, lambda alpha comma beta can be expressed in the following way: del lambda alpha by del u beta plus Christoffel symbol of second kind alpha gamma beta lambda gamma whole bracket du alpha ds. From the covariant differentiation of lambda alpha comma beta, we get del lambda alpha del u beta plus the Christoffel symbol of second kind alpha gamma beta lambda gamma du beta ds equal to 0. Now, if we multiply with du beta ds, we get d lambda alpha ds plus Christoffel symbol of second kind alpha gamma beta du gamma ds du beta ds equal to 0, because lambda gamma can be written as du gamma ds. Therefore, from this expression we can see that tangents are parallel along the arc length S. So, the curve becomes a geodesic. So, when del lambda alpha del S equal to 0, the curve on a surface is a geodesic. So, we shall not consider this particular type of curve. So, we consider the second option, that del lambda alpha del S is orthogonal to lambda beta. That means, for general curve we consider del lambda alpha del S is not equal to 0, and so we are considering that del lambda alpha del S is orthogonal to lambda beta. That means, del lambda alpha del S is co-directional to mu alpha, where mu alpha are the components of unit normal vector to lambda alpha called principal normal. So, mu alpha are the unit vectors and they are normal to lambda alpha. Thus, we can write that del lambda alpha del S equals to kappa g mu alpha. Now, this kappa g is known as geodesic curvature of the surface, and kappa g is always greater than equal to 0. When kappa g is equal to 0, we get the previous option, that is del lambda alpha del S equal to 0. So, for general curve we consider kappa g always greater than 0. Now, we consider the relation epsilon alpha beta lambda alpha mu beta equals to 1. This is the orientation is kept by epsilon alpha beta. for lambda alpha and mu beta. Now, taking the inner product with epsilon upper alpha beta on both sides, we get epsilon alpha beta, epsilon covariant alpha beta, lambda alpha mu beta equals to epsilon upper alpha beta. So, from there we get lambda alpha mu beta equals to epsilon alpha beta. Now, again taking inner product by lambda alpha, that is the covariant vector, with lambda alpha mu beta, we get epsilon alpha beta lambda alpha. From here, as lambda alpha and lambda alpha is 1, so we get mu beta equals to epsilon alpha beta lambda alpha. Now, taking intrinsic derivative of the previous expression, we get del mu beta del s equals to epsilon alpha beta del lambda beta del s. Now, we know that epsilon alpha beta are the permutation tensors. So, their intrinsic derivative is 0. So, we can get this expression. Now, putting the value of del lambda beta del s in the right hand side, we get del mu beta del s equals to epsilon alpha beta kappa g mu alpha, is a covariant vector mu alpha, because we are replacing del lambda beta del s, where lambda beta is the covariant one. So, from the above expression, we get del mu beta del s equals to minus kappa g lambda beta. So, we can see that for the curves on a surface, we have only two Frenet formulae. One is del lambda alpha del s equals to kappa g mu alpha, and another one is del mu beta del s equals to minus kappa g lambda beta, where alpha beta are the surface index running from 1 and 2. That means we can express this one by del mu alpha del s equals to minus kappa g lambda alpha. So, just we have mentioned that the previous equation and this number 4 are called Frenet formulas for a curve on surface. And when del lambda alpha del s equal to 0, we have this expression d lambda alpha ds plus Christoffel symbol of alpha gamma beta du gamma ds du beta ds equal to 0. Now, this is the differential equation of geodesic on a surface. Earlier we have discussed about the geodesic on a surface, and we see that del lambda alpha del s equal to 0 will give the differential equation of geodesic on a surface. Now, we prove this theorem that the necessary and sufficient condition for a curve on a surface to be a geodesic is that its geodesic curvature is 0. That means, kappa g equals to 0 is the necessary and sufficient condition for a curve on a surface to be a geodesic. So, let us prove this one. From the previous expression, we have d2 u alpha ds2 plus Christoffel symbol of second kind alpha beta gamma du beta ds du gamma ds equal to 0, and we consider that the curve is a geodesic. We prove that kappa g equals to 0. So, we can express the above expression in this form: d ds of du alpha ds plus gamma alpha beta gamma du beta ds du gamma ds equal to 0. Hence, we get du alpha ds comma beta, that means covariant derivative of du alpha ds with the inner product of du beta ds equals to 0, which implies that del s of du alpha ds equal to 0 by the definition of intrinsic derivative. Now, as du alpha ds is actually lambda alpha, so del lambda alpha del s is equal to 0. Now, from the Frenet formula, we know that del lambda alpha del s equals to kappa g mu alpha. So, del lambda alpha del s equal to 0 implies kappa g mu alpha equals to 0. Now, since mu alpha is a unit vector, so the components are not all 0, and therefore, we must have kappa g equals to 0. That is, the geodesic curvature vanishes. Converse will follow immediately. Just if we consider kappa g equals to 0, then we shall get del lambda alpha del s equal to 0, and from there we can see that the equation of the curve is similar to the equation of geodesic. That means, if kappa g is equal to 0, then the curve is a geodesic. Now, let us see an example that the condition for the u1 curve and u2 curve be geodesic. That means, the parametric curve, we are trying to find the condition whether the u1 curve and u2 curve will be geodesic, and the condition is that the Christoffel symbol of second kind, that is 2 1 1, will be equal to 0, and Christoffel symbol of second kind with 1 2 2 is equal to 0 respectively. So, let us go ahead to see that how it is coming. Now, from the previous expression of Frenet formula, we can easily find that kappa g equals to epsilon alpha beta lambda alpha del lambda beta del s. Now, for u1 curve, we have del alpha 1 equals to 1 by root a 1 1 comma 0. So, the components are 1 by root a 1 1 and 0. So, kappa g 1, that is the geodesic curvature for the U1 curve, will be epsilon 1 to lambda 1 del lambda 2 del s, and others will be 0. So, kappa g 1, if we put the values of this expression, we get kappa g 1 equals to root a 1 by a 1 1 to the power 3 by 2 gamma 2 1 1. Similarly, for the U2 curves, the geodesic curvature kappa g 2, that means U2 curves, we have epsilon 2 1 lambda 2 del lambda 1 del s, and others will be 0. And if we put the values of del lambda 1 del s, lambda 2 and epsilon 2 1, we are getting the geodesic curvature for U2 curve will be equal to minus root a 1 by a 2 2 to the power 3 by 2 gamma 1 2 2. So, the U1 curve and U2 curve will be geodesic if and only if the gamma 2 1 1 equals to 0 and gamma 1 2 2 equals to 0 respectively. Now, consider the surface of the sphere as an example, and we consider x 1 equals to a cos u cos v, x 2 equal to a cos u sin v, and x 3 equal to a sin u. And we are considering the curve on the sphere of the form u equals to u and v equals to s by a cos u 0, where s is the arc parameter. Then the geodesic curvature is tan u 0 by a. Now, we shall see that how this one is coming. Now, from the equation given above, we get the first fundamental form d square equals to a square du 1 square plus a square cos square u 1 du 2 square. We know how to find this first fundamental form in the previous chapter. So, we get d square equals to this expression, where a 1 1 is a square and a 1 2 is 0. That means, the curvilinear coordinate system is orthogonal for this sphere, and a 2 2 is this one, a square cos square u 1. Now, if we find the components of the unit tangent vector lambda alpha, that is du alpha ds, along the given curve, then lambda 1 and lambda 2 have the components 0 and 1 by a cos u 0. The non-vanishing Christoffel symbols are gamma 1 2 2 is cos u 0 sin u 0 and gamma 2 1 2 is minus tan u 0. So, if we just calculate the Christoffel symbol of first kind 2 2 1 and 1 2 2 and take the product with A upper 1 1 and A upper 2 2, then we get these results. So, del lambda 1 del S, the expression of del lambda 1 del S will be equal to this one, gamma 1 2 2 lambda 2 lambda 2, and del lambda 2 del S can be expressed in the form of gamma 2 2 2 lambda 2 lambda 2. So, if we put the values, we get kappa g mu 1 equals to, we are putting the values 1 by a square tan u 0, and kappa g mu 2 we are getting 0. Since mu alpha are components of unit principal normal vector, so we can write A alpha beta mu beta equals to 1. Now, if we take the multiplication with kappa g for both the mu alpha and mu beta, we get A alpha beta kappa g mu alpha kappa g mu beta equals to kappa g square. So, putting the values of alpha beta as 1 and 2, we get A 1 1 del lambda 1 del S whole square equal to kappa g square. Therefore, kappa g square is equal to tan square u 0 by a square. So, we are putting the values of A 1 1 and del lambda 1 del S in the above expression. We are getting this kappa g square. Hence, the geodesic curvature of the curve on the surface, that is on the sphere, is given by tan u 0 by A. So, here we have obtained that how the geodesic curvature can be calculated for a given curve on a particular type of surface.
Action.
So, in module 2 of chapter 7, we have learned about the Frenet formula on surface. That means, we have obtained the Frenet formula for a surface curve, and where we have seen that there are only two Frenet formulae for a curve on a surface, from where we have also deduced a new type of curvature called geodesic curvature, and we have obtained the necessary and sufficient condition for a curve to be geodesic on a surface. We have also seen an example that how to find the geodesic curvature for a curve on a given surface. So, with these things we end this module of chapter 7.